Okay, welcome to the mini course on virtual synchronous machines. My name is George Weiss. Can you see me well?
Yes.
Yes, we can.
So, my name is George Weiss, and I work here at Aviv University. And my research concerns control theory and power electronics. And I have been working on this topic of virtual synchronous machines for maybe 11 years now. Well, not only on this, but I have been working on it. And so I have been asked to give you an introduction to the topic. It will not be a high-flying research presentation. It is a I thought it is more useful if I make it a very basic introduction, so that you guys, I suppose that most of you are new PhD students, and okay, some of you maybe are already experts in power electronics or in electric machines, so I apologize to those. They might find some parts very boring. But I want to give you a basic introduction to this area. This area, which is converters connected to the electric power grid, and how they should be controlled, why they are needed, and what are virtual synchronous machines. So there are many things that I have to introduce. So I think that first I give a very general, a few words of what is a virtual synchronous machines, just on a very basic anecdote level, yes, without formulas. And then later I will move to give you some basic knowledge about inverters. And then later I will move to give you some basic introduction to synchronous machines. And then combining these two, I will give you some basics about virtual synchronous machines, how they are built. And then hopefully we will also reach, this will not happen all in these first 2 hours, yes, but we have in total 7 hours. And then I will also hopefully reach the stage where I can tell you why these machines are useful in a power grid. So let's start with a very general introduction. At any stage during this course, if you if something is not clear that I said, do not wait for the end of the hour. Tell me immediately, so you can unmute your microphone. Can you hear me well? Hello?
Yeah, we can hear you.
Okay.
Yes,
so
we can hear you.
I have to be careful to be close to one of these two microphones that are hanging from the ceiling here. So when you have a question, if something is not clear, don't be ashamed, don't be embarrassed, just unmute your microphone and ask me immediately what is the problem, because otherwise you lose track with what we are doing. So please do that. Okay, now you know that we all depend on the electricity grid, and the electricity grid is probably the most complex system that has been built by mankind. So this system has uncountably many branches and subsystems connected to it. So it is an extremely complicated system, which by a miracle works. And this has a long history. It has developed it started to develop about 140 years ago. And there were some real genius pioneers who started to develop the AC power grid. I mentioned Nikola Tesla and Westinghouse, I forgot his first name. And today it is difficult to appreciate how what a huge jump it was to invent this system out of nothing. What a leap of genius it was to design a three-phase generator when nothing of that sort has been known before. Today we are used to design things and write a model for them and test the model in Simulink and adjust the parameters and so on. But these people had nothing of that sort, and they had to invent the concepts. They had to build them. It was very difficult out of no available materials, and then they had to do experiments that showed that indeed it works, and it was a huge achievement that we cannot really appreciate today. Anyway, this system, they were sort of lucky, the people who developed synchronous generators, because, okay, you can sort of understand how one generator works. It is on an intuitive level. I think that most of you already have encountered synchronous generators, and on a very basic level, you know how they work, but we will talk about it in a moment. So you can sort of understand how one works. And then they started, I think it started in New York. They had a generator and they provided power to the street lighting of a few streets. And then others have seen that this is a great thing, and they did it too. And then the question arose, what happens if we connect two generators together? It seems like a crazy idea because each of them generates a sine wave, and then if two sine waves are not synchronized with each other, then that will create a huge current flowing between the two generators, and will destroy the two generators unless there are fuses which protect them. So the strange thing was that if you connect the two generators to each other in a very careful way, you cannot just connect it like you connect your iron into the socket. You have to do it in a very careful way. But if you do it in a careful way, so that they are at a moment of connection, they have to be synchronized, then a miracle happens, and these two generators remain synchronized, because there will be torques acting on both rotors of these generators, which will act in such a way that they will keep the synchronism between these two generators. So in other words, if any of the two wants to move away from the other, let's say move ahead or remain behind, there will be a torque which will fight against it. Of course, it can happen, but there will be a torque which, if this torque is, if the torque which tries to desynchronize the generator is not too large, then the two generators will remain in synchronism as long as operating conditions are within certain reasonable bounds. So this miracle was discovered. Now, let me tell you something very strange. We know the equations of synchronous generator. Of course, we can never write the equations in a totally precise way, because every model is an approximation of reality. There is always something that we have neglected. But let's say that to a reasonable degree, we know to write the equations of one synchronous generator. And then let's take this very simple case of having two generators connected together, and you want to prove that this system is stable, meaning that as long as the consumers are not too big, the consumers connected to these two generators are not too large, and as long as the torques acting on the two generators are within reasonable bounds, then the system remains stable. This is a basic fact which was observed maybe 130 years ago. And we know the equations. The equations were known already 100 years ago. And there is no proof. Even today, there is no proof that two generators connected together will remain stable. So there is a huge gap between what we know from experience and what we can prove mathematically. And so this science of understanding the power grid relies, of course, we do a lot of computations and formulas and we prove certain things, but at the same time, you have to develop feeling for it, intuition for it, because a lot of things you cannot prove, you can only sort of understand on an intuitive level what will happen. So it is not like mathematics. In mathematics, you have to understand step by step everything, otherwise you get nowhere. Here, it's always an equilibrium between understanding something intuitively and accepting that you cannot prove it, and also, of course, proving certain things. Okay, so the electric power grid developed, and it developed as a three-phase grid because having three phases has a lot of advantages over having one phase. And the main advantage of having three phases over having only one phase, and I will only mention this advantage, is that if you connect a three-phase generator to a three-phase consumer, then as long as this consumer does not change its property, so as long as the consumer is constant, will result in a constant power flow. If you do the same with a one-phase generator connected to a one-phase consumer, then the voltage will be a sine wave, the current will also be a sine wave, and the product of the two will be like sine square, which means it will oscillate at double the frequency of the generator. And that we don't know, we don't want that. In a big generator or in a big motor, we don't want the power to oscillate because it would introduce vibrations and stress on the equipment. We want this constant power flow, and constant power flow can be achieved if you have a three-phase generator and three-phase consumer. Okay, now we move ahead 130 years to our days, and you know that a lot of power is now generated from renewable energies like wind and solar and tidal energy. And also there are lots of so-called distributed energy sources, which are not necessarily renewable energy sources, but they are small generators located near the consumer for different reasons. One, to save on the transport of the electricity, and two, to make sure that even if the external grid fails for some reason, then you still have a local generation in, let's say, in a village or in a factory or in a hospital. You want to make sure that electricity is supplied even if the external grid fails for some reason. So you have these many, many little generators, and some of these little generators, they produce power at a frequency which is not synchronized with the grid. For example, many local generators, distributed generators, provide sinusoidal voltage at a much higher frequency than 50 Hertz. So that's one problem, that some generators from physical considerations, for physical reasons, rotate much faster than 50 hertz, and so they cannot be synchronized to the grid. Another one are wind turbines, which rotate according to the speed of the wind. So they are, in many cases, I wouldn't say always, but in many cases, they also generate voltages which are not synchronized to the power grid. And then the way to inject this power into the power grid is by converters. A converter is an electronic circuit which takes, an inverter. An inverter is a special type of converter. So an inverter is a special type of switched power converter, which takes power from DC and transforms it into AC. For our mini course, we are only interested in three-phase inverters, which have at the output sinusoidal voltage of 3 phases. And of course, the 3 phases are phase shifted by 120 degrees against each other. So any two are phase shifted by 120 degrees. So because we have now a lot of distributed generation, including renewable energy, we have a lot of inverters connected to the power grid. And then the question is, does this miracle that I described to you, the miracle of synchronization, does this happen also with inverters? Because if it doesn't, then the power grid will not maintain the synchronism. It will not maintain its stability. And in short, the answer is that mostly this is not true. So, of course, it depends how the inverter is controlled. Yes. So the inverter, you have many different algorithms for controlling an inverter. And if let's say that for most of the algorithms that are now used, this will not be the case, which means that an inverter knows to synchronize to a given grid. So if you have an already existing powerful grid and you come with an inverter, then of course, every inverter that is commercially available knows how to synchronize itself to this given grid and then inject power according to the power requirements that the user can tell this inverter how much power to inject. But if you take two inverters, nothing else, just two inverters, and connect them one to the other, like 130 years ago they did with two generators, then most of the time these two inverters will not know how to synchronize to each other, and it will not work. And why is that? When an inverter connects to a power grid, then it takes the power grid as a given. So it regards it like a voltage source. And it just synchronizes its own current so that the current injected to this power grid will be proportional to the given voltage, so that the power injected will be positive. Yes, because if the voltage is proportional to the current, then the power will be positive. But what happens if there are stresses acting on this power grid? For example, a sudden change of overall load on this power grid, or a sudden disconnection of a generator, or the sudden failure of a power line. All these events will force the generators in this power grid to suddenly change their behavior in a way which maintains the stability of the power grid. So, for example, if the frequency of the power grid suddenly goes down because a big consumer has connected to the power grid, or because a big generator has disconnected from the power grid, both of these events lead to a drop in frequency, then all the big generators will know to compensate for that by giving more power. And they have to give this additional power immediately. So when the frequency starts to drop, within a millisecond, they have to feel it and give more power. This phenomenon is called inertia. The decrease of frequency, the fact that the frequency is decreasing, so the derivative of the frequency will cause a certain power which is proportional to the derivative of the frequency. This is the inertia effect. And this inertia effect prevents a very sudden change of the system frequency. Another effect, which is similar, but it's not the same, is that if the frequency of the grid is too low, lower than what it should be, because there is a certain nominal value for the frequency, and if the frequency is less than this nominal value, then again, the existing generators have to give more power. Now, this sounds very similar to what I said a minute ago, but it's not the same. Here, the additional power is proportional to the difference between the nominal frequency and the actual frequency. And what I said a minute ago, the additional power is proportional to the derivative of the frequency. It's not the same. It's two different effects which sound similar, but both are needed in order to keep the power grid stable. There are also other elements in the behavior of big generators which help the power grid maintain its stability. And these bits of behavior, I mentioned two of them, right? The frequency droop, and the inertia. I mentioned two properties. There are a few more. These properties are usually not shared by inverters. They do not have these properties. That means that if you have a power grid where most of the power comes from inverters, and you have such power grids, then that power grid could lose its stability if the inverters are not controlled in a clever way. I said a moment ago that there are power grids where most of the energy comes from inverters, and the famous example is Denmark, where indeed most of the energy comes from renewable sources, but it is wrong to say, okay, look, the power grid of Denmark works, because Denmark is not an isolated power grid. Denmark is part of a large European power grid. So even if in Denmark 90% of the energy comes from wind turbines, that still is only a small part of the European power grid, where you have big generators that take care of the stability of the grid.
Do you know whether
So,
do you know whether they did like analysis, how much they can put in percentage of inverters?
yes, so various people have tried to work out what percentage should be allowed in a power grid to come from inverters. And of course, this is not mathematics. You cannot give a clear answer. But they did all sorts of simulations. And they took also some safety margin. And they came up with a rule of thumb that they said in a power grid, it should be no more than 30% of the power should come from inverters, based on various simulations. Now, of course, this number is very vague, and it does not take into account that inverters can be controlled by different algorithms. So they presumably, they have based this number of 30% on inverters working with most conventional algorithm, the oldest inverter control algorithm, which just tells, which works like this. You have a phase lock loop which synchronizes with the grid, so you detect the precise frequency and phase of the grid, and then you you operate the inverter as a current source, such that the currents are proportional to the voltages. That is the most basic algorithm for controlling an inverter. And presumably this figure of 30% is based on this algorithm. But this is the algorithm that you find today in most inverters. Yeah? Now, the aim of virtual synchronous machines, so virtual synchronous machines, and I will use the abbreviation VSM. So the aim of this is the following. You have an inverter which is not friendly to the grid. It does not help the grid to stabilize, but then you change its control algorithm in a complicated way, which I will try to explain, so that this inverter behaves like a synchronous generator. So in other words, if you have an inverter which is controlled by a control algorithm that is called VSM, then this inverter, from the point of view of the grid, this inverter becomes a synchronous generator. So so it does not degrade the robustness of the power grid. Quite the contrary, if you have VSM, then it can actually improve the stability, the robustness of the stability of the power grid. You can actually achieve stabilizing effects using a virtual synchronous machine that are actually even better than the stabilizing effects of synchronous generator. Because once you have this control algorithm in which you choose the parameters of this virtual synchronous machine, you can choose these parameters to be better than the parameters of a true synchronous machine, so that you can actually, using virtual synchronous machines, you can reach 100%, a grid with 100% supplied by inverters. So the objective of this mini course is to explain you the basics of what is a virtual synchronous machine. So this was this very vague introduction that I wanted to give. And now I will continue by giving you very basic introductions to various things, so that we can then combine them and understand how a VSM works. So the first thing that I want to explain to you is inverters, three-phase inverters. Yes?
I just wanted to, because you started with a question that went to inverters.
Speak louder. Speak louder.
Yeah, you started with the question that if there are only two inverters and they're connected together, they may not synchronize. So like, what was the answer to it? Will they or they will not? And they'll need this.
So if we have two inverters, which are virtual synchronous machines,
Then it will.
and we connect them together, then they will synchronize.
So then you can have an entire grid with 100%.
Yes. Yes, that is the purpose. Yeah. Okay. So introduction to inverters. Very basic. I apologize again to those of you who are already experts on inverters. So please take the lecture notes for week 6 in power electronics, which I have mailed to you yesterday, which Zuking has mailed to you yesterday. Yes, you all have the lecture notes, right? It is called week 6 because it's only one bit of a series of lectures on power electronics, which I teach occasionally. Yeah, everybody has it.
Yes.
Okay, and let's go straight to page 7. So if you look on page 7, you see that it is a description of 3-phase inverters, topologies, and operation. Yeah, you all see that. Yeah.
Yes.
Okay. Now, I'm actually sorry, but I have to give you a little background, which goes from an earlier lecture, which I did not send you, but it's really very short. So it is the canonical switching cell. So a canonical switching cell consists of 2 switches: a capacitor and an inductor. Okay, this circuit, which I have shown here, is called the canonical switching cell. And most inverters, most converters that exist are actually built from building blocks which are canonical switching cells. So maybe it doesn't look like this when you look at the electric diagram of some inverter, but if you think about it, then you recognize that inside this complicated topology that you see are actually one or several such canonical switching cells. So this is the basic building block of converters, of the switched power converter. It's not entirely true. There exist nowadays also converters which are not built out of canonical switching cells. For example, switched capacitor converters. But these are sort of esoteric things. So the most converters are built like this. What is the idea here? These 2 switches, let's call them S1 and S2, they are operated very fast in such a way that this point here, let's call it G, the point G is connected at any moment either to V plus or to V minus. And then V plus is a positive voltage with respect to ground. So there is a ground. V plus is higher than 0. And V minus is a negative voltage. It is less than 0. And the point G is connected at any moment either to V plus or to V minus. So that means that the voltage G with respect to ground will look like positive, negative, positive, negative. Then maybe the proportion changes and now it's like this. Sorry, never mind. Okay. Okay, so this is the output from this. I mean, this is a voltage G. This is G as a function of time, and usually this the frequency of these switchings up down is usually much higher than the frequency band that is of interest to us. You know, in every circuit, in every system, there is a frequency band of interest, and the switching here is higher than the frequency band of interest. For example, if you want here to obtain a sine wave of 50 Hertz, then the frequency band of interest is up to a few multiples of 50 Hertz, let's say up to 300. And then if you do this switching much faster, for example, you do the switching at 20 kilohertz, then that's much higher than any frequency of interest for the output signal. Now, this inductor will, on an intuitive level, it will filter this signal. So that how should I tell you? It's to this point V, you connect an external circuit. This external circuit can be, for example, but this is not part of the canonical switching circuit, but it can be, for example, a smoothing capacitor and a load. Or it can be a smoothing capacitor and an additional inductor and a load. It doesn't matter. There is some sort of circuit connected to the output of the canonical switching circuit. Now, this G, I can decompose it into a low frequency component and a high frequency component. The high frequency component is according to the frequency of the switchings, and the low frequency component is due to the fact that the proportion of time that the upper switch is connected changes. So there is a, let us say for simplicity, that the time between two moments when the point G is connected to V plus, so this time between two such moments is constant, and let's call it H. And this H is then called the switching period of this canonical switching set. And then the time out of H that point G is connected to V plus is only a part of it, and that part we call it DH, where D is a number between 0 and 1. Let me make it strictly between 0 and 1. And this number D is called the duty cycle of the canonical switching set. And this duty cycle, of course, changes in time. And let me also mention here that this could be also equal to 0. Okay. And the time that the switch will be in the opposite position, meaning at V minus, will of course be, so this time here, this time, when the point G is connected to V minus, will be 1 minus D times V minus. So you see that if you look at the average over one
But is it supposed to be 1 minus D times V minus or times H?
sorry. I'm sorry. The time is 1 minus dH. Yes, that's what you wanted to say, huh?
Yes.
Okay, now let us see what is the average voltage on the point G over one full switching period. So it will be for a time dH, it will be equal to V plus, right? So this will be G average. And then for the remaining time, which is 1 minus D times H, it will be equal to V minus. So now I have taken the integral of the voltage over the whole switching period. But this integral, I have to divide it by H. In order to, divide it by H in order to obtain the average voltage. So this is very easy to divide by H because we have H inside. So it is equal to dV plus 1 minus D times V minus. So this is the average voltage. Yeah. Now, the controller, which controls this canonical switching cell, it controls the switches, of course, and it chooses this capital D. So by choosing this capital D, you see that we can vary the average voltage of G over one switching period. We can vary it between V minus and V plus. Yes. So G average is between V minus, if I allow here, so okay, because it's, I took strict inequality, so I have to take here open interval V minus and V plus. Now, if there is an external circuit connected here, then this external circuit will see, of course, the high frequency present in G, but it will see it through the impedance of this inductor, which means that at high frequency, at the switching frequency, this inductor has a very high impedance, so that the high switching frequency will have very little influence on this external circuit. But the low frequency component of the signal G, and I do here sort of a red curve to show you the low frequency component. So you see here in this region, the D is close to 1, which means most of the time in this region, most of the time the switch keeps G at the level V plus. Sorry, I did not mark that this is here V minus and this is V plus. Okay, so most of the time the voltage will be equal to V plus, and very little time it will be equal to V minus, which means that the average will be high. And then if I reach this region, you see here it will be only a little time up and a lot of time down. So here the average will be down, right? And then in my picture it goes again up again, and then again it goes down. It's a strange picture this way, but okay, that's what came out when I did the picture. So on average, so this red signal is the low frequency component of the signal G, which can easily pass through this inductor, the red signal, and the high frequency switching cannot easily pass through the inductor because the inductor has high impedance at high frequency. And so the effect of all this gain is that in practice, what we see at the output of the inverter is as if it would be only the low frequency component of the signal, which is G average, this signal, G average. So G average, we can say that this is approximately equal to G average if we neglect the high frequency component. And then our circuit consists of this inductor and whatever other circuit there is. And you can consider that the signal here, G, is approximately equal to G average. This formula for the average voltage should be explained together with the formula for the average current. There is a certain current flowing here, I. And you know that the current in an inductor cannot change suddenly, because L times the derivative of the current gives the voltage of the inductor, and the voltage cannot be too high. So that means that if we have here this current, let's call it I plus, and here is the current I minus. Yeah? Then obviously from Kirchhoff's laws, we can see that I is equal to I plus I minus. But on the other hand, we also have the following. This current I can be regarded as practically constant during one switching period. Yes, because the switching period is very short and the inductor current cannot change so quickly. Yes, so for this reason, we can say that during one period, we consider it to be constant. And then we have that I plus on average is equal to, so let's see, what is it? For a proportion D of the time, for a proportion D, this current I plus is equal to I, because the upper switch is closed and the lower switch is open. So all the current comes from the upper side and goes here. So I is equal to I plus for a proportion D of the time. And for the remaining time, the upper current is 0. So if I do the average, I get that it is D times I. Right? And of course, I minus will be equal to 1 minus D times I. Yeah? So these are the approximations which are used in a canonical switching cell, that for the currents you have these expressions, and for the voltage, for the low, this is of course the low frequency component of the current, because I averaged it. Yeah, and this is also averaged. So this is if I neglect the high frequency switching and I only look at average quantities, which means I work in low frequency, then I have these currents and I have this voltage in the point G. And this is the so-called average model of the canonical switching cell. So these currents, of course, you don't have to write the second. The second follows from this, from Kirchhoff's laws. It's enough to write I plus equal D times I. So this formula, together with this formula, is a so-called average model. Average model of the canonical switching cell. This together with it. Yeah? When you do simulations of a switch power converter, so you have in this switch power converter, you have several instances of such a canonical switching cell, and you don't want your simulation to run for days, then you replace the exact model of the canonical switching cell with this average model, and then this is a very good approximation, and the simulation will run much faster, And you will see the results will be, of course, much smoother because you have removed the high frequency oscillation. Yeah. Now, this was the preliminary about what is a canonical switching cell. Now we go to page 7 of the lecture notes, which I have given you. So, let's do first the simplest possible three-phase inverter, which is a so-called two-level inverter. What is a two-level inverter? If you look at the circuit diagram on page 8, if you look on page 8, I skip all the text which is on page 7, and we go to this picture. So in this picture, we have a very simple image of a three-phase inverter. So we have a DC voltage source, V plus and V minus, of which V minus could be equal to 0, but no, usually it's not 0. Okay, so usually V plus and V minus are symmetric with respect to what we consider the level 0. And then you have here a switch, a canonical switching cell. You see, this is a canonical switching cell. Capacitor, 2 switches, inductor. Yes, that's exactly what we had there. Now we repeat it. We have another canonical switching cell. And we repeat it a third time. So now we have 3 canonical switching cells which share the capacitor C. So this capacitor C, which we had in the canonical switching cell, is common to the 3 canonical switching cells. And here, in the really simplest configuration, this is the simplest possible inverter. So this is an inverter. You see that each canonical switching cell will produce here a voltage which is as if you see the average voltage at point G. So let's call this GA, GB, and GC. And this is now, let's say, VA, VB, and VC. This will be connected to some circuit. For example, it could be the power grid, or it could be an electric motor. Very often you have such an arrangement to drive an electric motor. This is then called a brushless DC motor. When you have this circuit, precisely this circuit, connected to a synchronous motor, that is called a brushless DC motor. Yeah. So whatever you have some circuit connected here. And then this circuit, which is connected here, sees as if you have the average voltages here, which come to this point through the inductor L. Yeah. If you generate GA, so GA, the signal GA and GB and GC, we usually denote the 3 phases by A, B, and C. So the signals GA, GB, and GC are, of course, ugly signals which have a lot of switchings in them, like I drew it here. But they can be approximated by their averages. Let's say GA tilde, GB tilde, and GC tilde, G tilde are short time averages, short time averages of G. So that means the actual signal GA looks very ugly, like this switching up down very fast. But the averages, which are G tilde, they are computed according to this formula, and they could be sine waves, for example. In most cases, we want them to be sine waves. So G could be low frequency sine waves. What do I mean by low frequency? I mean low in comparison to the switching frequency. Yes, if the switching frequency, let's say, is 20 kilohertz, then if I generate here 50 hertz, that is then very low compared to the switching frequency. Okay, so this is a most basic inverter. Now, this most basic inverter is indeed what you find in brushless DC motors, because a brushless DC motor has to be very compact and cheap and simple. But if you do a more complicated inverter, for example, for connecting solar power to the grid, then it will not be like this. It will have a lot of extra elements, which I will explain to you after the break. So let's take now a 10 minutes break. If you have questions, please ask. It was okay. So we continue. Yes.
I want to ask one question. What decides the rate of the switching cells and the kind of switching cells?
The rate of the switching.
Yeah.
The designer fixes this rate. So you decide to use. Your controller is programmed to work at a certain frequency.
So it depends on what kind of low frequency output we want. And
it depends also on the frequency range of the output that you want. So, for example, if you want output of 50 hertz, then you also have to be able to control the harmonics, let's say up to the sixth harmonic, so that's 300 hertz. So you want to have a good control in this range up to 300 hertz. Then if you choose a switching frequency, let's say 10 kilohertz, that's good. That's because it's far enough. You can control very well anything that happens up to 300 hertz and even further if your switching frequency is 10 kilohertz. Yes, but if you want to create a canonical switching cell which produces a signal for a loudspeaker, a very powerful loudspeaker, and then the output frequency range is up to, I don't know, 15 kilohertz, then you need the switching frequency to be much higher.
And is there like an order, like if you choose, if I want 50, then you said 10 kilohertz is okay. If the output is 50 hertz.
So in general, the switching frequency should be at least 10 times higher than the highest frequency that you want to be able to control. Okay, and then once you have decided this switching frequency, then you build your controller in such a way that it executes an algorithm with that frequency. So let's say you have decided that you switch at 10 kilohertz, then you have to have a program which controls this converter, which is executed every 100 microseconds, because that means that the program is executed at a frequency of 10 kilohertz. And at each run of the program, the program will decide new values for the duty cycle. For the duty cycle, yes. So at each execution, the duty cycle will be generated by the controller. That is the output of the controller, the duty cycle. And this duty cycle then goes to a special circuit called a PWM generator. Okay, I should have explained. Thanks for pointing it out. So the more complete picture is okay. Let me show you a more full picture of canonical switching cell. And then also I had a question from one of your colleagues, from Kevin. I want to answer that as well. So let's make more room here. This switch is typically, not necessarily, but typically, it is a MOSFET transistor. But it can be also something else. It can be, for example, an IGBT, which is a similar device. I mean, it's also a switching device, but more powerful and less fast. So what I have drawn now are two MOSFET transistors. And these MOSFET transistors are connected to a circuit which you buy it ready-made. It is a complicated circuit, which is a so-called driver. Can you read that? Driver. And here is another driver. And the driver has a logical input, so it's a binary input, which is the PWM signal. Yeah. And when this signal, the input to the driver, when it is high, it means you want to close the switch. So it will give a high gate voltage. So the gate voltage here depends on the input signal to the driver. When this is high, then also this is high. But this is a logical signal. So it is typically between 0 and 3.3 volts, this signal. It comes from a processor. Whereas this signal is a gate signal for a MOSFET transistor. So it is typically of the order of 12 volts. So this is higher voltage and also much higher current. The current flowing here is very high. I explain in a moment why. Whereas here it's only a signal, so it's very little current flowing here. So this is to be more precise, a gate driver. Gate driver. And this is also a gate driver. And then something else that I should point out is that here you have a diode. And this diode is called the body diode of this MOSFET transistor. You have it also here. And this diode is something that's unavoidable. It is part of the MOSFET transistor. So you cannot avoid it. It is part of the construction of the MOSFET transistor. And it is a bad quality diode, meaning that when it conducts, and then you want to stop it from conducting, so you want to switch it off, it will not switch off immediately. It will have some inertia. Even if you reverse the polarity of the voltage on this body diode, for a short time, for a very short time, it's a few nanoseconds, it will conduct in reverse direction. So it's a bad quality diode, which comes with the switch. And this is now the output, yeah? Now, so the story is like this. You want to avoid a situation in which these two switches are operated simultaneously. Because if you operate, I forgot to put back the capacitor. And your friend Kevin was asking me why we need this capacitor. So I will answer also that question. Okay, now here is I plus, here is I minus, here is V plus, and here is V minus. Okay, so we have recovered now the picture, but you see the picture has become more complicated because I have shown more elements which must be there. Now, why did I say that the current here is high? Because this gate of the MOSFET transistor is like a capacitor. So it is as if you have a capacitor between this gate and the source, which is here. Yes, this is gate, this is source, this is drain. Now, you have a capacitor here, and you want this signal here to be very sharp. You want it to go up very fast and then to go down very fast, because you want to close and open the switch very fast. Why do you want to close and open the switch very fast? Because in the transient, while it is neither closed nor open, so it's in this transient time, it consumes power. That's when the switch gets hot. During, well, most, it gets heated during this switching, because if I show you the voltage on the switch, it goes up like this. Yes, if I zoom in time, this is a voltage on from drain to source, right? It goes up not suddenly, but if I zoom in sufficiently much, then I can see that this rise of voltage is gradual. And during this time, when the voltage goes up, obviously the current goes down, because what I'm showing here is a process of turning off the switch. So the voltage goes up when I turn off, and the current goes down. This is the current. Now, you see, before the switching, the voltage is high, but the current is low. So the product of the two is, the current is practically zero. So the product is, the power is practically zero. And after the switching, again, you have here, the voltage is almost zero and the current is high. So the product, the power again is very low. It's not entirely zero, but it is very low. But during this transition, the power is high. So if I draw here the picture of the power as a function of time, then here it is very small. During the transition, it is high, and then it is again small. Yeah. So there is a big power during the switching. Yeah. The switching can take several tens of nanoseconds. So you want this switching to be short, and this is why even if you switch at, let's say, 10 kilohertz, which is not so high, but still you are usually searching for the fastest switch, which can operate at I don't know how many megahertz, because you want this switching to happen very fast, because then your losses will be small. The losses in practice mean that the MOSFET transistor becomes hot. So in order to make this switching fast, you need that this signal, the gate signal, should go up and also down very fast. But there is this capacitor here, which means that you have to charge or discharge this gate capacitor very fast. And even though this gate capacitor is not big, it can be something of the order of 1 nanofarad. But if you want to charge or discharge 1 nanofarad in a few nanoseconds, then you will see that that can lead to currents of several amps. So this gate driver must be an amplifier which can provide currents of several amps for a very short time, but it has to be able to provide very high current. And so this gate driver is not an easy, not a simple circuit. If you naively think that you can do it yourself to build a gate driver like I was some years ago, then you have a bad experience with it. Luckily, these days, nobody does it. You just buy a gate driver. But this took a long time to develop good gate drivers. Then another problem which appears in such a canonical switching cell is that the power supply to the upper gate driver, this is called the upper gate driver, and this is called the lower gate driver. The lower gate driver is not a problem because you have to give it a voltage with respect to the V minus, because the voltage, the gate voltage is measured with respect to the source. So this is a gate. The gate voltage is measured with respect to this point. So you have to give it, let's say, a 15 volts power supply with respect to this point, which is fixed, which is constant. So you give here a power supply which is between this point and this point, VCC, yes? And that will give you the corresponding output voltage with respect to this reference voltage on the gate. But what happens with the upper gate driver? The upper gate driver, its reference is this point, the source of, the drain of this transistor. Then you need to generate this signal with respect to this reference point, which means you have to give the power supply, you have to give it VCC with respect to this point. Now, this point is not constant. This point, you remember, it's going up, down a lot. So you have to generate here a voltage supply with respect to a very, very unstable, not unstable, but non-constant, a very, very non-constant, very fast changing reference voltage, which is this point, the point G. Remember, we call this point the point G. So the simple solution to this problem is to give a floating power supply. A floating power supply is a power supply which is not connected to, so the input is connected to some DC power source, and the output is entirely disconnected from the input. So there is the floating power supply, then you can connect it between these 2 points, and the floating power supply does not care that this point goes up and down hundreds of volts, because it is not connected to anything. It's floating, so it will move along with this voltage. The floating power, the ground of the floating power supply will move along with it. Yes, it will not feel it. So that's one. The simple solution is to give floating power supply to the upper gate driver. There are also other more clever solutions where you do not use a floating power supply, but instead you you take for the power supply, you take you put a capacitor and you charge this capacitor each time when this point is down at 0. So you have a let's draw a picture. You can hear, I am getting now into technical details which are not what I intended to teach. You have here a capacitor, and you know that, and this is here connected to this point. Now, from time to time, this point G is sometimes at the bottom, sometimes it is at the bottom. Whenever it is at the bottom, then you take voltage from the same power supply VCC, let's say 15 volts with respect to this point, and through a diode, I don't have place where to do it, through a diode, you charge this capacitor. So when this point G, when G is down at the level of V minus, then this diode can supply from VCC, it can charge this capacitor. When this point G is higher, then the VCC level, which is close to V minus, is lower than the voltage here, so the diode will be blocked, and the gate driver has to survive on the energy stored in this capacitor. Yes, so this is the story of the power supply for the higher gate drivers. Now, what about these diodes? These diodes show that the voltage G can never get higher than V plus, and it can never get lower than V minus, because just think about it, if G would ever get higher than V plus, then this diode would turn on, and it would short circuit whatever voltage is here to V plus. So these diodes are called also freewheeling diodes. I don't know why. They prevent the voltage G from exiting the range between V minus and V plus. Now, another technical detail, which is here, I already started to tell you that you have to prevent at all costs, you have to prevent that the two switches should be closed at the same time. Because if they close at the same time, then you have a short circuit from V plus to V minus. Yeah, and that will destroy both switches. So you have to be very careful that in the circuit which generates these PWM signals, that it should not have, it should never happen that they are both at the same time logical one. But this is not enough, because if you, let's say the upper switch has a logical one up to this moment, and the lower switch, which should be the complement of the upper switch, because you connect G either to V plus or to V minus. So when this goes down to 0, the other one should go up, right? So this is a logical signal on the, how should we call it? Let's call it L1 and L2. So this is L1 and this is L2. So one is on up to a certain moment, and then the other turns on. So this is a logical 1 level. This is 1, and this is a logical 0 level. Yeah. Sorry, this is time. Okay. Now, what happens at this moment when one goes down and the other goes up? There will be this transient, which I have shown you here. One will start going down, the other will start going up, which means that during this transient, the current can flow through both switches and create a short circuit. Yes, it's a very short time, but it can happen, and this can destroy the circuit. So how do we prevent this from happening? We have to put a dead time between them. So that means if this signal L1 has stopped being high, then the next signal will go high a little bit later, a little bit later. You see, there is a difference. There is this difference here, which is called dead time. Dead time. So this is meant so that you make sure this dead time can be, let's say, 100 nanoseconds. It depends on how fast the switches are. If the switches are very fast, you can make the dead time smaller. So you see, this dead time is here so that the upper switch stops conducting, and you have to give it enough time to stop conducting before you start conducting with the lower switch. Yes, of course, you do the same dead time also in the opposite direction. When you disconnect L2, I mean the second switch, and connect the first switch. So on both sides of the switching, you have to allow this dead time. And the PWM generator, so you have this circuit, which is a PWM signal generator, which very often is part of your processor. So that is already programmed to allow this dead time. And you can also adjust this dead time. So it's one of the parameters in your program to adjust this dead time.
So it's that part of H, the H that we have there on the.
Oh,
the
this
dead time
happens within.
within
All this
H,
happens
right?
within
Yeah.
H. So H is much longer. H is, let's say, here.
Yeah, yeah.
So this happens within one switching period. Yes.
So you don't really have DH and 1 minus DH, but you have like.
You have
You have these.
okay.
dead
wait,
time.
wait. You have the dead time. You have the dead time in the PWM signal.
Okay.
But with respect to which part is conducting, the upper or the lower, you do not have a dead time. That's where the diodes come in. Because let's say that you have a current flowing in this direction, and now and it came from here. So it came from here through this switch and goes out here. Yeah? And now you want to switch it. You want to stop this switch from operating, so you want to switch it off, and you want to switch on the lower switch. So you give a dead time. So you have switched this off, but you have still not switched on the lower switch. But you cannot stop the inductor. The inductor will create a huge voltage if you try to stop its current. So the inductor demands the same current also during the dead time. So where will this current come from during the dead time? It will come from this diode. Yeah. So when you are in the dead time, then in fact, from the point of view of the system, you are already connected to the lower voltage, to V minus, because now the current will come from this diode. So you are in fact already connected to V minus during the dead time. And the same in the opposite direction. Yes, if originally the current was coming from here, and now you are in the dead time, then it will, this happens when the current flows in the opposite direction. Then the current flows this way. Then when you disconnect from here, then the current will already start flowing through the body diode to V plus. Okay, so the dead time is meant to protect the switches, but it is still true that the point G at any moment is connected either to V minus or to V plus. Even during the dead time, it is connected through one of the diodes. Now I'm coming to the question of Kevin. So Kevin asked me, why do we have this capacitor? And this is because look at the current. The current, this current I, for a proportion dH, where is it shown? Here, during this proportion of time dH, the current comes from here, Yes, so the current at this point looks like this. This is a time dH. Yes, but from the for the external circuit, I want that this canonical switching cell should look like a smooth circuit operating at low frequency. So on this side, I have achieved it with this inductor. The high frequency will not be able to go through this inductor. So from here, I see it as if it's only the low frequency. The same thing is achieved on this side by the capacitor, because you see this high pulse of current will be smoothed by this capacitor. And if I look here, then it will be an almost constant current. So this is I plus in time. Here the current is almost constant, but here after the capacitor, inside I see pulses. Yes, but I don't want to see pulses from the outside circuit. From the outside circuit, I want to see everything smooth. So the smoothness is provided here by the capacitor and here by the inductor. Okay? Okay. Sorry?
Yeah, I thought that if you increase the switching frequency, then maybe you would have smoother curves, smoother waveforms.
Yes, that's true. That's true. The more you increase the switching frequency, the more smooth it looks from the outside. So if you look at the circuit from the outside, from here and from here, the higher the switching frequency, the less you feel the switching frequency, because it's filtered out. But there is a cost of going to very high frequency. The cost is precisely these losses in power, because this loss is a given. I mean, if the voltage is given and the current is given, then each switching costs you a certain amount of energy. This integral of the power, this is the amount of energy that it costs you one switching. And if you switch fast or you switch slowly, I mean, if the switching frequency is high or low, the amount of energy you waste in one switching is more or less the same. So if you switch very fast, then you waste a lot of energy into the switching.
Oh.
Okay, now let's go back to the inverter. This board is very hard to erase. Didn't earn my salary. Okay. So remember, we have here 3 canonical switching cells. So now you know that each of them has a lot of drivers and body diodes and power supplies for the drivers, all that. So that's all here, but we don't draw it. And here now come a lot of additional circuitry can be put. So this is the most basic diagram. But for example, in many inverters, we also want to have a powerful neutral connection, which means a connection to the neutral line of the three-phase grid. I come in a second to why that is sometimes needed, but let's say that that is needed. So we need a powerful, we expect strong neutral currents. If we do not expect strong neutral currents, if we expect only very weak neutral currents or none at all, then we can just work like this. But if okay, or we can, okay, there is a solution for putting a very weak neutral current. We can put here 2 capacitors and 2 resistors in parallel, and say that this midpoint here, this is our neutral. And these resistors, we choose them large so that the power consumption of these resistors will be not important. And these capacitors, so these are the neutral capacitors and the neutral resistors. And the role of the neutral capacitors is to keep the neutral line stable with respect to V plus and V minus, so that it will not drift to, let's say, the neutral line could be very close to V plus or be very close to V minus, which would prevent the inverter from properly functioning. Because you remember the output signal, which is the average of the switching signal, it can be at most V plus, and the minimum is V minus. The output voltage G, GA, GB, GC, when you average it, it has to be between V minus and V plus. Now, what happens if this midpoint drifts? Let's say it drifts. Let's say that the midpoint, for some reason, for example, because there is a DC component present in the current, it drifts and the midpoint is here. So 0 is here, V plus is very small compared to this reference, and V minus is very big. If you are in this situation, then you can only give a very small sine wave. Yes, up to this level. You cannot get higher. So you cannot give a sine wave of the amplitude that you wanted to give. Or if you try, then you are in trouble, because then you hit the upper boundary and you cannot go higher. So your sine wave will be clipped. It will be clipped, and then you can go down, and again here it will be clipped, and so on, which is a situation you don't want, because such a waveform has a lot of harmonics. Yes? So you want to keep the neutral line in the middle between the positive and negative terminals of the power supply. If the current that you expect to flow in the neutral line is small, so what is this current? If this is IA, this is IB, and this is IC, and this current flowing back is I neutral, then it's clear from Kirchhoff's laws that I neutral must be equal to IA plus IB plus IC. Yeah? And if you expect to have a balanced load or a balanced grid, then this sum should normally be equal to 0. And so such a very simple circuit will do the job. But what happens if you expect a significant neutral current? When could that happen? When is it possible that we expect a significant neutral current? Let's say that you have a backup generator, a backup power supply for a hospital. That's such a backup power supply is usually called a UPS, an uninterruptible power supply. So the UPS starts operating when the main power grid fails. it detects that the main power grid has failed, and then it will take energy from a battery, so it has a battery storage, and it will take energy from there, and through an inverter, it will continue to supply electricity to this hospital. So this is a very common device which you can buy rather cheaply in many places. So suppose you have this UPS, and it's connected, of course, to the 3 phases inside this hospital. But you know, in the hospital, most consumers are one-phase consumers. So in each socket, you have only one phase. Now, it's true that they distribute them in such a way that in one room it will be phase A, and in the next room it will be phase B, and then phase C. So they try to balance it. They try to have approximately equal load on the 3 phases, but this may not work out exactly. Sorry?
It's outside.
So let's say that suddenly some consumer, even an air conditioner, it's still one phase, starts operating, and it's connected to one phase. That means that suddenly you have an additional 2 kilowatt on one of the phases. Now, this means that the phases are not balanced. The sum is not 0. Yes, this sudden increase of 1 kilo, let's say it was balanced up to that moment, and then suddenly connects a one phase 2 kilowatt air conditioner to phase A. Then there will be suddenly 2 kilowatt flowing through phase A, and all the rest has been balanced. Yes, so this will now come here, and you have a significant current that has to flow through the neutral line because it is this sum. Yes, so that significant current corresponding to 2 kilowatt cannot flow through these resistors and capacitors because these are small capacitors and big resistors. It cannot. It will create a very big. It just cannot flow through. Yeah, and so you have to provide a more complicated circuit, which is shown on page 8 of the lecture notes that you have. So the more complicated circuit would be to add one more canonical switching cell. With a neutral inductor. So this is the counterpart of this. Yeah? And then you also have capacitors here. And this would be now your neutral line. Now, what is the advantage of this circuit is that you can have, if you need it, so this is a neutral current here, IN, which is this, yeah. So this neutral current comes now here, and it flows into a canonical switching cell, and there is no limitation. It can be a very big current flowing into the canonical switching cell, and you try to control the canonical switching cell so that the average voltage here, let's say call it Gn, you try to keep Gn equal to what you call 0, what you call the average between V plus and V minus, you call it 0. Let's say that's your definition of this. So you keep this Gn at this 0, which is the average between V plus and V minus. And in this way, the capacitors will filter out the high frequency switching noise, and then this point will be kept at the middle between V plus and V minus. Yeah. this strange additional circuit, which has a whole theory how to control it, which I will not go into. This is a relatively complicated solution, but if you want to keep the neutral able to absorb a big current, then you have to do it. What additional circuit may appear here? You see, one inductor on each phase does not have enough of a filtering effect. Usually, people put a filtering capacitor to ground on each phase. So this is CF, CF, CF. And then they put a second inductor. So not everybody does that, but if you want a good quality filtering, then you put a second filter inductor. And you connect your output voltage here. Such a so-called LCL filter, which I have now shown you, LCL filter, is more efficient in filtering out the high frequency component of G than if you just use one inductor or one inductor and one capacitor, which is called LC. Usually, so there are inverters which only use LC, and better quality inverters use LCL. And very low quality inverters, but often you do not need more than very low quality. So for example, inverters that operate brushless DC motors, they don't have the capacitor. They have only the inductor. Yes, because there is no need. The brushless DC motor, I mean the synchronous motor inside, does not care if you give it a highly oscillating voltage, because it filters it out by itself. The motor filters it out. So in the case of a brushless DC motor, the capacitor is not needed. In most inverters, you have the capacitor, and in good quality inverters, you have LCL, and you have even more circuits, which I will not describe now, which prevent common mode voltages from propagating from the inverter to the outside world. We don't discuss it. Okay, now, I'm nearing the end. We usually distinguish between voltage mode inverters, where the control algorithm controls the output voltage G, and current mode inverter, where the control algorithm controls the output current. Okay, you have to compute, when you have a filter, you have to compute the resonant frequencies of the filter, because this is a dangerous point. You see, LCL filters are not damped. They are resonant circuits. So they have resonant frequencies. And you want to put the resonant frequency of your filter to be between the frequency of interest that you want to obtain and the switching frequency. So, for example, if you want to obtain here 50 Hertz and your switching frequency is 10 kilohertz, then you take these two frequencies on a logarithmic scale, 50 Hertz and 10,000 Hertz, and you put the resonant frequency of the filter in the middle, but in the middle on a logarithmic scale. What does it mean? The middle between 2 points on a logarithmic scale. If you have on a logarithmic scale, you have the frequency of interest, let's say the grid frequency, and you have the switching frequency, and you want to take the midpoint between the two, then that is square root of FG Fs. Think about it. If that is not clear to you, why on a logarithmic scale the midpoint between 2 points is a geometric mean between those two. Now, why do you put it in the middle? Why the resonant frequency? Because you want to generate here low frequency voltages at the frequency FG. So if the resonant frequency is significantly higher than FG, then your signal will not excite the resonant frequency of the filter. Let's say you have between 50 hertz and 10 kilohertz. The midpoint is roughly 1 kilohertz, right? So the 50 hertz signal will not excite the resonant frequency of 1 kilohertz in your filter. And on the other hand, the switching frequency will also not excite. Yes. So that's why you want it to be neither of the two. Yes. You want the picture is like this. Up to the resonant frequency, the filter will let every signal pass, and then it will go down. This is a body amplitude plot. Yes. Output voltage against input voltage. And at the resonant frequency, it will start going down at a slope of 40 dB per decade. Since there is no damping, there will be a high peak. Well, there is always some damping, but not big. So there will be a high peak here, like this. Yeah. You want that your low frequency signal, which is FS, should pass unhindered through the filter. So that you are in this region where the signal passes unhindered. Yes, this is 0 dB. And you want that the switching frequency, which is here, Fs, should be strongly damped, strongly suppressed. So you see here, you have a very low level for the transfer function, which means that this is strongly suppressed. Yes. So you want the resonant frequency to be between the useful frequency and the switching frequency.
That is FG. The left.
Oh, I'm sorry. This is FT. Yes, FT. Yes. Okay. I think we have to stop it here. I did much less than what I thought I will do, but that's always what happens. But we meet again in the afternoon. In 2 hours time. In 2 hours time, we meet again. Yeah.
You mentioned that there are two kinds of inverter: voltage mode and current mode.
Yeah.
That there can be like some inverters where both are the control parameters.
I'm not sure what you mean by that. Okay, let's stop the recording here.